Good day, everybody. In this week's experiment, we'll be working on the preparation of Rochelle salt. First, you'll watch the video and we'll show you how to synthesize Rochelle salt in 2 steps. In step 1, we show you the decomposition of sodium bicarbonate to generate sodium carbonate as the product. In step 2, we'll use the product from the first step, which is sodium carbonate, to react with potassium bicarbonate to generate Rochelle salt. Rochelle salt is also known as potassium sodium tartrate. As you might have noticed if you look at the name or the formula, it has 2 cations, and this type of salt is so-called a double salt. Rochelle salt also has some other special properties. One of the interesting property is so-called piezoelectricity, which is the ability for a certain material to generate alternating current when subjected to mechanical stress or vibration. After you have carefully watched the video, we are going to talk about chemical stoichiometry, which is the quantitative relationships between reactants and the products in a chemical reaction. In this process, we're going to go over the details about how to calculate the theoretical yield, percent yield, and the grams of one reagent needed to react with another.
Okay guys, for the first part of the experiment, you have to weigh out your sodium bicarbonate. So you have to know the exact mass of this you're starting with. You start by tearing the balance. See how that sets the balance to 0. Then you're going to weigh the empty reaction vessel. Your reaction vessel is this big test tube. So you weigh the big test tube, get the mass of that. Okay, now that we know the mass of our empty test tube, we add our sodium bicarbonate to it and we weigh it again. Okay, now we're going to carry out the reaction where we change our sodium bicarbonate into sodium carbonate. To do that, all you have to do is heat it up. It decomposes and it gives you carbon dioxide gas. And we do it in this device. You could do it without this device, but what this does is it lets you see that you are indeed carrying a reaction out. When I heat this up, it's going to make carbon dioxide gas, which is going to force this water over here into the beaker. So as I heat that stuff up, you should start to see water flow into this beaker. And that, again, is that carbon dioxide gas creating some pressure on this system. So, can you see how it's making the water come out there? And it's draining this flask. So this is really just to prove to you that the reaction is taking place. Also, this lets you know when the reaction's done. If there's no more water coming over, the reaction's done. Now, we'll probably drain this flask. How do we know when the reaction's done? Well, after it's drained, we'll see little bubbles of CO2 coming out. No more bubbles coming out, that means the reaction is done. So we're just cooking up our sodium bicarbonate, and we're going to be left with sodium carbonate. Now the reaction's done, but you see water droplets at the mouth of the reaction vessel here. So to get rid of those water droplets, you would simply heat it up, and that water should disappear on us. And that's the first part of the experiment, making the sodium carbonate. Okay, the second step in making the Rochelle salt, you're going to react potassium bitartrate, that's this material here. It's also known as cream of tartar. It's used in cooking. So you're going to react your potassium bitartrate with the sodium carbonate we made previously. So we weigh out our potassium bitartrate. So to weigh out our potassium bitartrate, we put a little piece of weighing paper on the balance and we zero it. Then we pour our potassium bitartrate in till we have the desired amount. We have 3.995 grams of the potassium bitartrate there. We'll transfer our potassium bitartrate to the large beaker. So here's our potassium bitartrate. We need to add some water. So the procedure says to add about 1 milliliter of water for every gram of the potassium bitartrate. It won't dissolve, it'll just kind of make a sludge. And there's our potassium bitartrate suspended in water. We heat it up by placing it in this hot water bath. And to get the reaction going, we have to add our sodium carbonate from with sodium. Okay, here's my sodium carbonate from part A. We've weighed it on the balance. Now we're going to transfer it to a weigh boat here. And there's the sodium carbonate I'll be working with. Your instructor may want you to weigh it in the weigh boat, use it, and weigh it again. It depends on if you're going to complete that part of the report sheet. Now we'll take our sodium carbonate and react it with the sodium bitartrate that we have here in the hot water bath. You can see how as we add it, they react quite vigorously, making that bubbling and fizzing. If I add just enough sodium carbonate to completely react with the potassium bitartrate, the solution should go clear. It's a little bit tricky. You want to go kind of slow near the end, just little portions of the sodium carbonate, and hopefully you can get the solution to turn into a nice clear solution. And here I'm adding some more sodium carbonate, and that last little bit I added, seems to have made the solution turn to a nice clear solution. Here's my solution now, and you can see how all of that potassium bitartrate has dissolved after it's reacted with the sodium carbonate. Okay, so here's my Rochelle salt. There's some little specks of unreacted sodium carbonate in there. So what you want to do is take your small beaker, weigh it while it's empty. Then take your Rochelle salt solution and pour it into here and try and leave any solids behind. So any solids that were in here are left behind, and here is my product. Here's my Rochelle salt dissolved in water. We'll just let this cool off, and hopefully we'll get some nice crystals. Okay, and here's our product. After it's been sitting in the ice bath for some time, we start to spontaneously get crystals of the Rochelle salt. Sometimes you won't get the crystals spontaneously. Sometimes you have to put in a teeny little crystal of Rochelle salt from somebody else's prep to get the ball rolling, and then it crystallizes quite rapidly.
Let's first look at how to calculate the theoretic yield and percent yield for the formation of sodium carbonate. We did this in the first step in the demonstration. The chemical reaction that is involved in this process is listed over here. In this chemical reaction, as you can see, 2 moles of sodium bicarbonate or sodium hydrogen carbonate or baking soda, they are exactly the same thing, will decompose to make 1 mole of sodium carbonate and 1 mole of carbon dioxide and water, respectively. To calculate the theoretical yield for the product sodium carbonate, we need to go through a 3-step conversion as clearly listed over here. Here's what we have to begin with. First, we have grams of sodium bicarbonate, which is what we weighed out in the first step of the experiment. You weigh this out and you want to convert this to moles of sodium bicarbonate. That's our first step. Okay. Second step, because moles of sodium bicarbonate, which is listed over here, is related to moles of sodium carbonate. By looking at chemical coefficient, as you see, it's 2:1 ratio. That 1 is not written, it's implied. So that's our second step. In the third step, we convert moles back to grams. Okay. Remember, for each step, we can use a unit conversion, okay, using a conversion factor. For the first step, this relationship between grams and mole is called molar mass relationship. Molar mass of sodium bicarbonate is already provided as listed as 84.01. The second step, look at its moles versus moles. That's the molar ratio as determined by the balanced chemical reaction. So this is a molar ratio. How do you get this ratio? You get this from the balanced chemical reaction as listed over here. As we clearly indicated, it's 2 moles of sodium bicarbonate versus 1 mole of sodium carbonate. The last step, we are converting this moles of sodium carbonate back to grams of sodium carbonate. And for this last step, step 3, the relationship is mole versus grams. That's also called molar mass. So if for one chemical reaction, right, as we can see over here, if we started with a certain number of grams, for example, 1.500 grams of starting material, sodium bicarbonate, how do you calculate the theoretical yield for the product sodium carbonate? As we analyzed, first step, we started with 1.500 grams sodium bicarbonate. Then you need to cancel out the grams. You use molar mass. As we can see for step 1, we use molar mass as the conversion factor. But do make sure grams of sodium bicarbonate is canceled out. This is our first step. For second step, we use molar ratio. Okay, molar ratio, these numbers 2 and 1, they come from, this 2 come from over here. And this number 1 come from over there. Okay, they are chemical coefficients, the numbers before the chemical formulas. As we can see, after the second step, this is canceled out. All right. The third step, we use molar mass again, but this time we need to cancel out this moles of sodium carbonate. That's why we need to use moles of sodium carbonate as the denominator for step number 3. Okay, let me change the color. Step number 3, we're going to use moles of sodium carbonate as the denominator, so they cancel out. After 3 steps, we are able to calculate the theoretical yield, or the maximum theoretically can be generated in this reaction. Okay, so if you do your chemical reaction, you might use different numbers of grams of starting material. For example, what if I change this? What if I change this number 1.500 to a different number? Okay, so if we change that number to a different number, if you change it to different number, let's say, what if I change this number to any number, right? We are going to provide you with the data. So let's say, what if I started with 1.654 grams? How do you calculate the whole thing? The procedure is exactly the same, except that rather than using 1.500 grams, we're going to use 1.654 grams. Okay, then everything else actually stays exactly the same. No change at all. And you do your calculation, you can figure out a different number. Rather than having 0.946, you will have a different number over here. All right. So we just showed you step by step how to calculate the theoretical yield for the production of sodium carbonate. To calculate the percent yield, we use the actual yield divided by theoretical yield. So what is the actual yield? To remember, when you run the chemical reaction and try to collect the product, there will for sure be some loss of the product. You will never be able to collect the 100% of the products that is generated. For example, if we have not collected the maximum amount, which is 0.946 grams of sodium bicarbonate, rather we collected a small amount, say 0.938 grams of sodium bicarbonate. So what is the percent yield? The amount that is collected is actually so-called actual yield. So actual yield divided by theoretical yield times 100 gives you the percentage. We have 0.938 grams divided by 0.946 grams times 100. That gives you 99.2% yield. In reality, this reaction is a very high yield reaction. The percent yield is very close to 100%, but it should never be over 100%. As you have seen in the lab demonstration, in step 2, we use the sodium carbonate. We use the sodium carbonate to react with potassium bitartrate to generate the Rochelle salt. In this balanced chemical reaction, you are asked to calculate how much product can be generated. Okay, the product is your Rochelle salt. So we follow very similar procedure to example 1. First, to calculate the final grams or theoretical yield of Rochelle salt, you need to start with the number of grams of one of the starting material, which is potassium bitartrate. Okay. First step, you convert grams to moles. And for this step 1, apparently it's grams and mole relationship. So that's why this is so-called molar mass. Molar mass, you calculate the formula mass. 1 mole is formula mass grams. But here it's provided to you already. Okay. Second step, you convert moles of potassium bitartrate to moles of your Rochelle salt. Okay. And it's molar-molar relationship, and this step 2 is the molar ratio. How do you find the molar ratio? The molar ratio or mole ratio can be read through the balanced chemical reaction. So in this case, it's 2 to 2 ratio because that's 2 moles of reactant versus 2 moles of product. That's how you get these number 2's over here. Right. For step 3, it's mole of product converted to grams of product. For this step 3, it's mole and the gram relationship. That's called a molar mass. Okay. And the molar mass of Rochelle salt, you add all atoms together, which is provided over here, 282.22 grams per mole. So let's carry out this whole calculation. You start with 3.500 grams of potassium bitartrate, the starting material. That's where you start over here. Right. For the first step, the molar mass, you need to put it in the position where you can cancel out this grams of starting material, potassium bitartrate. Right. Then the second step, when you set it up, second step, you have the mole relationship. Do make sure the mole of potassium bitartrate can be canceled out. That's why for the second step over here, you have 2 moles of sodium, potassium bitartrate at the bottom because they will cancel out. Similarly, for the next step, okay, for the next step, you need to be able to cancel out this product. That's why in the last step, the mole of Rochelle salt is written as the denominator. After you are done with the whole procedure, calculate it, and you will have 5.249 grams as the theoretical yield. As I mentioned, similarly, in the data we're going to provide you, you will have a different number than 3.500 grams. So how do you do your calculation? Let's say the number you have over here is not 3.500. Rather, you have 3.950. If it's 3.950 grams, okay? When you do your calculation, the only number that you're going to change is this 3.500. You replace that number with your own number, which is 3.950 grams. Again, this 3.950 is just an example. We will provide you with a different number for your calculation. Then you do your calculation, you'll get a different number. It's not going to be 5.249. All right? Okay. For the percent yield, for the production of a Rochelle salt, it's very similar. It's going to be, let me erase everything. So we have actually not collected 5.249 grams. If you collected less than that, okay, of course you're going to collect it less. It can never be more than theoretical yield. So 3.596 grams of Rochelle salt is what we actually isolated from the reaction. To calculate the percent yield, we use the actual yield to divide by the theoretical yield times 100. It turns out to be 68.51%. This yield is actually quite high. In example 2, we just showed you how to calculate how much product can be generated. So that's the product based on the amount of starting material. In this example 3, I'm going to show you if you are given certain amount of starting material, can you figure out how many grams of the other reagent is required for the reaction to complete? So how many grams of sodium carbonate is needed for this reaction to complete? In order to relate these two chemicals, we do this in very similar fashion. First, you start with the number of grams of your starting material, and you convert it to moles of the starting material, which is then related to the moles of the other reagent or reactant, then convert back to the grams of sodium carbonate. Similarly, for step 1, it's grams to molar, so that step you use molar mass. Step 2, you convert molars to molars. It's based on the balanced chemical reaction. So when you look at this chemical reaction, this is 2 molars versus 1 molar. Okay, so that's why you have 2 and 1 over here. For your step 2, that's the molar ratio, which you read from the balanced chemical reaction. For your last step, when you look here, your last step is converting moles to grams. That's molar mass relationship. So the whole procedure is very, very similar. Okay, if you use the same amount of 3.500 grams of the starting material. Of course, did you notice that this 3.500 grams is exactly the same amount as what you used in example 2? Because that's the same chemical reaction we are using for the calculation. Okay, it's not a coincidence. It must be exactly the same, right? So similarly, if you use a different number, for example, rather than using 3.500, if you had a number, let's say 3.950 grams. When you do your calculation, the only change you should make is to replace your 3.500 in this example with your number, 3.950 grams. As I just emphasized, we will be providing a new set of data for you to do your calculation. Here is just to demonstrate to you how the calculation is done. So this concludes this week's experiment. Have a good day. Bye. For the lab report that is due next week, you will need to turn in page 163 through 165. As you can see on this page, we have provided all the necessary data for your calculation. Please complete all the other blanks and turn them in. For the next page, we also have all the data you do need for the calculation. So that's it. See you next time.